The next type of word problem we're going to look at are type of word problems that are called uniform motion problems. Every single one of the problems in this section are going to be based off the formula D is equal to RT, or distance is equal to rate times time. Right? How far you go is equal to how fast you were going times how long you were going at speed. Now there's going to be two types of uniform motion problems that you're going to see. One thing moving, or two things moving. Cool. All right, so these two different types of problems. With the one thing moving, I'm actually not going to give you an example of this because it's so straightforward, it's simple. If you only have one thing moving, then generally you're given two of the three things up here, like you drove 400 miles in 8 hours. How fast were you going? So you just plug in the two pieces of information that you know, solve for the last. Those are very, very straightforward. The ones that get very difficult are the two things moving. In fact, these are the ones that almost all like the math jokes are made about. You know, two trains leave Chicago, one's going east, one's going west. How many pancakes can you cook in an hour? So let's see if we can handle a few of these, because these are rather tedious to get through. So let me just put one of these up here. Let's see. Let's say two cars leave New York at the same time. One heads north at 60 miles per hour. The other south at 70 miles per hour. Let's see, how long until the cars are 390 miles apart. Okay, now I'm going to point over there a lot because that's where our outline was for the last thing. We're still going to follow the same outline. We're just going to make a slight modification to it. We're still going to read the problem first. Here we're talking about two cars driving around, so we know it's one of these motion problems. And since we have two things moving, it falls into the, well, two things moving category. So we get the idea what's happening. What's important up here? Well, the north car is going 60 miles per hour, southbound car is going 70 miles per hour, and we want to know when they are 300 miles apart. So that's going to be the important information there. Step 3 says set up your variables. Now, what we're getting ready to do, technically you don't have to do, but you're going to find that you get a lot more success if you do. I'm really going to kind of combine step 2 and 3, kind of what I've already done up here, and some variables into a table. Now the table is going to represent the things moving, so our northbound car and our southbound car. The columns here are going to represent the variables in our equation, right? Distance is equal to rate times time. So the information we put into these problems is information that's only specific to that vehicle. So what do we know about the northbound car? Do we know the distance it drove? No, nowhere up there does it say the northbound car drove 100 miles. Do we know how fast it was going? Yeah, we do. We know the northbound car was going 60 miles per hour. And how long did the car travel? Well, the question's asking for how long, so we can be pretty sure we're going to have variables in the time column. All right, let's go to the southbound car. We don't know how far it drove. We do know it was going 70 miles per hour. And again, we have no idea how long it drove, and that's part of the question, so we know we shouldn't be able to fill that in anyway. All right, so you notice we end up, and this is pretty common how these work, we end up with one column of just information from the problem. Now the next column is generally going to be a column that has the variables in it. And the question says how long, so we know we're looking for time. So in the time column is where our variables are going to go. Now, just like before, since we have no idea how long either one of these cars travel, I'm going to put the variable right there. Now you can use an X if you want. I'm going to use T for time. Now I know they're both T because if you think about how this problem worked, they both start in New York at the same time, right? Because we said they start at the same time. And they start driving away from each other. At some point in the future, they're supposed to be 390 miles apart. So they both leave at the same time, and then sometime in the future, they're going to be 390 miles apart. So they both drive the same amount of time. So the way that these almost always work, notice we got one column of information, one column of variables. Now the last column is always created using our formula. We know distance is equal to rate times time. So how far did the northbound car go? Well, 60 times t, so its distance is 60t. The distance the southbound car went was its rate times its time, which would be 70t. Okay, so if you kind of look at this picture over here, the one I just sketched really fast, this red distance right here, now this is a distance, is 60t. This distance down here would be 70t. So you can see from the picture here, the distance the northbound car went plus the distance the southbound car went has to be equal to the distance between them. So I'm going to go ahead and write our equation. The distance the northbound car went plus the distance the southbound car went has to be the distance between them. Right, again, notice I said that as a sentence, because if the sentence makes sense, then the math behind it should also make sense. All right, this is just a linear equation. Let's go ahead and see if we can solve this. This is 130t is equal to 390. Divide both sides by 190, so t is equal to 3. Okay, now what did t stand for in this case? And yeah, I know it's time, but it ended up being the time for the northbound car and the southbound car. So to answer the question, the northbound car drove for 3 hours and the southbound car also drove for 3 hours. All right, let's try another one. Let's see here. Do I got enough room? Maybe. So let's see. Hey, it's a jogger runs by person in the park. An hour later, the person sees the jogger has dropped their wallet. He gets on a bike and goes after the jogger. If the jogger is going 5 miles per hour and the, let's say, biker is going 10 miles per hour, how long until the biker catches the jogger? All right, longer written problem. That way we got a lot to make our way through here. So let's see, a jogger runs by a person in the park. An hour later, the person was just laying there realizes, hey, that jogger dropped their wallet. So he gets on a bike and heads off after the jogger. Now, if we know the jogger is running at 5 miles per hour and the guy on the bike's going at 10 miles per hour, how long until the biker actually catches up to that jogger? So we read the problem. Hopefully we realized that this was a motion problem because we got things moving around. And we got 2 things moving around. So let's go ahead and make ourselves a table. Anytime you have more than one thing moving around, this table can be very helpful. All right, now remember the columns here are distance, rate, and time. We have a jogger and the biker. All right, now remember, information that goes into here are only information that's specific about each individual. So we don't know how far the jogger went. We don't know he was going 5 miles per hour. And we don't know exactly how long the person was jogging. The biker, again, don't know how far he went, but we do know he was going 10 miles per hour. Again, don't know how long the biker had to bike to catch the jogger. Now, the question, once again, in this type, asks for how long. So we know somewhere in the time column, we're going to have some variables. Now, this is slightly different from the other one because, well, they didn't start at the same time, right? The jogger was already jogging, and an hour later, the biker decides to go after him. So since we don't know anything about how long the jogger jogged, we could call that T. Now, since the biker left an hour later, he traveled one less hour of time. So this would be T minus 1. All right, now not to make this confusing, it was pretty arbitrary which one of these two I put first. I could have put biker first and jogger. It wouldn't have mattered at all. But if I would have done that, then I would approach this question slightly differently. I would have said, well, I don't know anything at all about the biker, so I could have called the biker T. And then I would have said, well, how long did the jogger run then? Well, the jogger would what? Run an hour more. So we could have called this one T and this one T plus 1. So the red would also work as a way to set up the variables for this. And this is what it would look like if you probably would have put these in the opposite order. All right, let me get the red out of there so it's not confusing. All right, so if you notice, we have one column of information, one column with variables. So the last column we always get using the formula. In this case, distance is equal to rate times time. So the jogger went a distance of 5 times t. The biker went a distance of 10 times t minus 1. Okay, so there's our tables complete. Now this one again is also a little bit different because notice we've used all the information in the problem here. In our last problem, we knew something about a total distance, right? That they are like 390 miles apart, but we don't have anything else here. Well, if two things start at the same spot and end up at the same spot, basically one thing catches another thing, their distances have to be the same. So the distance the jogger went has to be the same as the distance that the biker went. So our equation for this would just be 5t has to be equal to 10t minus 1. All right, let's go ahead and solve this. Let's clear our grouping symbols. Move all of our variables to one side, so let's get all of our t's to one side. So I get negative 5t is equal to negative 10. Divide both sides by negative 5, we get t is equal to 2. All right, so now that we've solved our equation, we need to answer this question. Unfortunately, this is a poorly worded question because it says how long until the biker catches the jogger. It shouldn't be worded like this, but it's worded like this so we can kind of understand the problems you may run into when we're answering these type of problems. What do you mean, how long for who? Because they traveled 2 different times. So let's see how long each one of them traveled. The jogger traveled a time of 2 hours, or jogged for 2 hours, because that's what T is. So this person was running for 2 hours. How long did the biker bike for this problem? Well, that would be T minus 1, so that would be 1 hour. So, what's the answer to this question? Well, like I said, it's a poorly written question, so there's really not a specific answer. The way it probably should have been written, well, or hopefully in your book when you see it, would be something like, how long did the jogger run? Or how long did the biker bike? How long did the jogger run was 2 hours, the biker biked for 1 hour. But you do need to be able to figure out which one of those that the author is asking you for in this. All right, uniform motion problems, they are a bit more complex. There's generally a lot more information going on, so this table is really, really helpful. And in general, not always, because every word problem is different. In general, you're always going to get one column of information, one column where you're putting variables, and the last column you're using your formula to fill in. Now, whatever column you're using to fill in this case, we used our formula to get distance. Notice we used that to write our equation. Again, in this case, we ended up using our formula to figure out what distance is, and we used those distances to write our equation. That's pretty standard how these work. The only way that you're going to get good at these, though, is to practice.